In this video, we're going to go ahead and cover polynomials and how they relate to power functions, which you just learned about. So a polynomial, first of all, is a sum of these power functions, meaning you have a different term for each, between each plus, and each of those terms is actually a power function. We can write this using this notation that we have here, this ax to the nth power. Okay. However, after a certain amount of, terms, we might run out of letters. So what we do is we generalize it to look more like this one right here, where we can use the same letter but use something called a subscript. So this little n right here is a subscript. And as we're going down our polynomial here, you can see the subscript is just going down by 1, okay? Till we get to eventually, a sub 1 times x and a sub 0. As we're descending in this polynomial here, we can also see that the x part of the function, so this guy right here, is also descending in exponents. You can see the n here goes down by 1 here. The next one would be n minus 2, all the way till we get to our x squared, x to the first power, and then this one would be x to the 0. But since x to the 0 is just equal to 1, we don't actually have to write that last one, okay? Just like we also don't have to write the 1 here because x to the first power is still just x, okay? So a couple things are to take note of. You will be, we do recommend you copy these notes, the next ones that are coming up. It says that for these functions, okay, we start with the constant term, okay, meaning this is the number that does not have an x. So it's the one that I kind of notated here at the end, where we had a to the 0 times x to the 0, okay, because again, that x to the 0 is just equal to 1, and we have that right here again. This is called the constant. So here, this would be our constant in this particular polynomial that we have written here, okay? The constant coefficient, which is also our y-intercept. So for example, if you had like x squared plus 5, we know that the 5 is going to be where, the graph crosses the y-axis. So we'll get a little bit more into that in just a bit. The next term has x to the first power, okay? So you can see that that's going to be this term right here, which we usually just write as x because, again, the little 1 is kind of implied here, okay? Each additional term has the next number as its coefficient subscript as well as its exponent. So we have that. If you're going, to the left, it would be ascending order. In other words, each of the subscripts is going up by 1, and same thing with the exponents, is going up by 1. But once we get to the way end, okay, the coefficient at the end is called our leading coefficient. And this is actually the leading term. So I'm going to kind of, let's choose a different color here. This right here would be our leading term that is being discussed in this part right here. And the leading coefficient is the number that is in front, or a sub n, so to speak. Okay, so leading coefficient is that first number that's next to my highest degree term here. Okay, and that also tells us, notice that this notation allows us to have as many terms as we need, so we won't run out of alphabetical letters like I mentioned earlier. So, for example, we have this f of x equals 4x cubed minus x plus 3. Okay, so if this was our polynomial expression, polynomial function, our a sub 3 would be 4, so that you're looking at something like this, a sub 3 x cubed, okay, that's going to fall in line right here, minus a sub 2 x squared, or plus, doesn't matter. In this one, we don't have an x squared, that's why this one is going to be our 0 right there, okay? Minus a sub 1 x, okay? So you can see that right here we have that minus 1, which is where we get that negative 1 from. And finally, plus a sub 0, which in this case is equal to 3. So we have our matchup directly like so. A sub 0 is our 3. This a sub 1 is going to be that negative 1. A sub 2 is not there, so it's 0. And a sub 3 is 4. And that's exactly what I have here in these lines. Okay, so this is just an example of how you would line these terms up. Continuing on, we have that the degree n of a polynomial is the value of the highest exponent in the function. I'm sorry, in the polynomial. I keep saying function, but I guess it's the same thing in this case. So, for example, okay, let's say we had something like, and I'm just going to make something up all crazy like, let's say we had 2x to the 5th power plus 3x to the 7th power minus 8. I don't know, I'm just making this up. So in this case, you can see that this is not in order for one, because this is the biggest exponent. So you might want to rewrite it just to kind of, make it look a little nicer here. So this would be 3x to the 7th power plus 2x to the 5th power minus 8. And this just has it in descending order where our exponents are going from the biggest one to the smallest one. Okay, in this case, 7 would be first. So in this problem, my degree, okay, which is our n, would be equal to 7 because that is the highest degree, the highest exponent in this polynomial. Okay, moving on. The end behavior of a polynomial is the same as the end behavior of its leading term. Okay, so this is something that you should have learned a little bit about in the previous notes. When we're looking at end behavior, we're always thinking kind of these arrow things, right? It's one of the four. Okay, and what we're going to do to find this for these problems is look at the leading term. So again, as for another example, just to kind of show this here, let's say we had, I'm going to use y this time. Y equals, let's do 2x to the power of 5 minus 3x minus 7. And I'm just completely making these up. So I don't know the particulars of these functions, but I can more or less estimate, some of the items, such as our end behavior. I can tell where the end behavior is going to be based on my leading term. So here, my leading term, okay, my leading term is going to be this first guy right here, 2x to the 5th. So based on the end behavior for 2x to the 5th, that's going to tell me the end behavior for the entire polynomial here, okay? So I can see that my leading coefficient here is 2, so it's positive, which means that it's going to be based on my degree. Actually, let's look at the degree first. So my degree, n, is 5, okay, which is odd. So I know that odd functions are either like this or like this, okay? They're either falling on the left side, rising on the right side, or vice versa. Since my leading coefficient is positive, okay, I know it's going to follow this pattern right here. So for my end behavior for this one, let me use a different color here. So for the left side, okay, I'm going to have as x approaches negative infinity, okay, well this is happening. So y is approaching negative infinity. On the right side, as x is approaching positive infinity, well now this is happening. Y is going to infinity. Okay, moving on. Okay, so in this next part, we're going to be talking about the zeros of a polynomial function. And the zeros of a polynomial are actually the x values. So this is the x values where the graph meets the x-axis. Okay, these are also the points where f of x is equal to 0, or you can also think of it as where y equals 0, where f of x and y are the same thing, meaning that the x values are solutions to the equation f of x is equal to 0. So I have an example here just to kind of show what we're talking about here. And we're just going to draw a super quick graph. If I set each of these terms, and I went ahead and left it in this factored form, just to make it a little bit easier, okay? If I were to solve these and set these equal to 0, I would get the following. Well, so for the first one here, it would just be x equals 0 because, well, there's nothing else to do there. So x equals 0 is right here in the center. For the second one, so for this one right here, if I set this equal to 0 and I solve, I would subtract 3, and that's going to give me 0 there. So x is equal to -3 is my second, second 0. So that's about right here somewhere, so -3. And last but not least, x minus 3, if I set that equal to 0 and solve, again, I get 0 on the left side, so plus 3. So I get x is equal to 3. Oh, that did not come out so nice, did it? Let's fix that. So x will equal to positive 3, okay? And that's going to be on the other side. So we can see that these 3 points are on the x-axis, as mentioned up here. I cannot seem to draw a straight line or circle or a nice circle for the life of me, but that's okay. And they are also solutions because here at this point, this is also where f of x, or in this case y, we could say, is equal to 0. Okay, because any point on this line, y is equal to 0. And if you just want a little few more specifics, this graph actually looks something like that. Okay, so there you go. Quick little example. Moving on, the y-intercept of a polynomial's graph is the y value where the graph meets the y-axis. So again, stuff that you're already familiar with. In this one, we're going to add the verbiage here that it has the same value, okay, as the constant coefficient a sub 0. So remember that number we saw at the way end of that complicated looking polynomial? That is the same as our y-intercept. So again, for example, and I'm not going to do the whole thing here. I'm just going to make this I'm going to make it up. So let's say we have 3x to the 4th power plus x squared minus x plus 13. I'm just, again, making these numbers up. In this case, our a sub 0, okay, so our a sub 0 is going to be this 13 right here, this positive 13. So that means that on my graph, okay, wherever 13 is located, let's say it's just up here somewhere, my graph is going to go through that point. And this is, let's see, this is a even function, so it might look something like, I don't know, something like this or something, okay? Yeah, I'm not going too much on the specifics here. I want to focus more on this y-intercept. So my y-intercept is going to be 13 because that is my constant coefficient here at the end. Okay, and also at this point, f of 0 this is where 13 would be equal to our f of 0 here. Okay, because x is equal to 0 at this point. Remember, our x is always going to be equal to 0 anywhere on this line, and our y is equal to 13. So this is why this one works like that. Okay? All right. And finally, I think after this, we're going to do some examples, some more in-depth examples. We have 3 definitions here. A degree n polynomial has up to n factors. So whatever the degree is, that's as many factors that we're going to have in that polynomial that we can break it down to. So you can see here that we have a degree of 2, okay, degree of 2, and therefore there are 2 factors. Okay, using the same exact example, if we have n polynomial, degree of n polynomial, it also has up to n real zeros, meaning we're going to have no more than, in this case, 2 zeros. So our n is equal to 2, and we have 2 x-intercepts or zeros or solutions. Okay, and finally, a degree n polynomial has up to n minus 1 turning points. The turning point is where the graph will change direction. So usually you'll see something like a relative min or a relative max, and that's where the turning point will start. So for example, I'm just gonna, again, make this up. Let's say we had something kind of like this, okay? This is a cubic function, and we have a relative minimum here, so I'm just gonna put min. REL, relative min, and we have a relative max right here. Okay, so we have, if we were to count our turning points here, there are 2 of them. We have the graph changes from going down to up here, so this is kind of like 1, and then we have 2. So this one has 2 turning points. And I mentioned a few seconds ago that this is a cubic function, so it's some kind of power of 3, probably negative because I drew it backwards. And so in this case, for y equals, I don't know what the rest of it is, but it's some kind of cubic function. So in this case, our n would be equal to 3. Following this line of thought here, n minus 1 would be 3 minus 1, which is 2. That's exactly what we have here. Okay. Another way to think of the turning points that I think one of my students actually mentioned was it's the number of like little hills that we have. So we have 2 little hills here, and that's the same idea here with the turning point. I think that is it for this side. Yes, that's it. So let's go ahead and do some examples now. And you will have some of these to do on your own. So you might want to make sure you pay attention, copy everything down. Okay. We're going to fill out an example of 2 different types. We're going to have an even function. Okay, so remember, even is when our degree is an even number and it has that symmetry. This is actually one of the power functions. And we're going to do an odd function as well. Okay, these 2 up here are power functions. We're going to kind of extend the idea by adding a few more terms and making it look a little more complicated, but just showing you that, it's not so bad. So let's begin by just sketching the graph of our parent functions, our OGs, our original graphs here. We know that the x squared function does something like this. It is a parabola. Hopefully yours is nicer than mine, okay? And the symmetry of this function is even because it has y-axis symmetry, which by definition is even symmetry, okay? Our end behavior, well, we're going to look at each side here. So we're going to color coordinate just a little bit. As x approaches positive infinity, so this is our x right here, as we're going this way, f of x is going, well, if we look at what our graph here, f of x is doing, it looks like it's rising, right? So, and it's rising to infinity. So f of x is going to infinity, okay? Positive infinity. As as x approaches negative infinity, so now we're looking at the other side as we're going to, negative infinity over here somewhere on x, f of x is still rising, so it's still going to infinity. Okay, let's go ahead and do an example with this type of function. So a general polynomial, let me zoom down just a little bit more. We'll come back up for the odd in just a bit. Oh, I just kind of gave you the answer there. General polynomial expression and example. So we're going to come up with an example that has these, I guess you could say, properties, okay? So let me get a different color here. We'll just make it nice and general. Let's do 3x squared, okay? What else? Plus 6x plus 1. And I'm just kind of making this up, okay? So if this is our polynomial expression, okay? I guess this is an expression, not a function in this case. If this is our expression, then the degree for this one, okay, the degree for this one looks like our highest exponent is that 2. So our degree would just be 2. Okay. The leading term is going to be this entire term that is with my highest exponent here. So it's going to be that 3x squared. Okay, I'm going to go ahead and write it in terms of the a subscript 2. Okay, so a subscript 2 x squared. Let me write that actually a little bit darker. That's kind of hard to see with this blue. So a sub 2 x squared. And in this case, we're going to match that up again, like I said, with our 3x squared. Okay, the leading coefficient then, if this is our leading term, is just going to be that 3. So this 3 right here. So it's going to be our a sub 2, which in this case is 3. Okay, as easy as that. For the next part, we're asking for the max number of factors and zeros. So remember that the max number of factors is going to be the same as our degree, same with the zeros. So since our degree is 2, okay, this is going to be the same as our degree, which in this case is just 2. The max number of turning points, on the other hand, is going to be equal to our degree minus 1. Or you could think of it like n minus 1. So in this case, it's going to be 2 minus 1 equals 1. Okay, so these are all some of the properties we could get just based on what we know so far. So the last part is going to ask us to go ahead and sketch a possible graph of a polynomial with this max number of turning points, and then go ahead and label the turning points, I guess, as far as 1, 2, 3. Okay, so for this one, I'm going to go ahead and say, since it only has one turning point, let's see, we'll use this color here. Since it only has one turning point, I know that it's going to be either like this or like this, okay? So just to be a little more detailed, I'm going to look at my leading term and see, well, it's a positive 3, okay? So since it's positive 3, I know that the end behavior should be going up. So I know that the end behavior is going to be doing something like this, okay? So I'm going to say my parabola might look something like that. And we can see that the turning point in this one is going to be right here, this little hill right here, okay? All right, to be more specific, I guess you could say it's right here. I'm just generalizing. There we go. So there you have an example of an even function and how to fill this out with some of its properties, okay, some of its traits. Let's go ahead and look at the odd function now. And this one is going to be odd because we have that power of 3. So we have this power of 3 here. So x cubed is our OG for the cubic functions. And we should remember that this one does something kind of like this. It has a curve going upward, and then it goes downward this way. Probably not so crooked like mine, but you know, something like that. And this is going to be an odd function with odd symmetry. We also call this origin symmetry, okay? Because if you were to rotate it 180 degrees, it would look unchanged. Okay, so just like the one before, we're going to find the end behavior. So again, as x is approaching positive infinity, so as we're going to the right here, it looks like my graph is going up to infinity. So infinity and beyond, okay? As we are going to the left, so as x is approaching negative infinity, as we move this way, okay, our graph is falling. So it's going to negative infinity. Okay, so a little bit different than the first one. Moving on, we're going to go ahead and construct an example for this one. So let's say we have for this one, let me go ahead and change colors here real quick. We want a general polynomial expression example. So let's see, x to the power of 3, okay, plus x squared minus 4x plus 1. Okay, and in this example, since I chose this one, it looks like our degree, okay, so our degree for this one is going to be this little 3 right here, because it's the highest exponent, so our degree is 3. Okay, our leading term, just like the one before, is going to be kind of like this one, but now we have the third, you know, x exponent, if that makes any sense. So we're going to have a subscript 3, and then we have x cubed. And in this problem, it looks like this term right here, okay, is 1x cubed, or just, x to the power of 3. We don't have to put that 1 necessarily, but if you do, it's not a big deal. You can put the 1 if you want to. Our leading coefficient then is going to be that 1 that we don't see. So it's this 1 right here. So it's going to be a sub 3, and in this case, a sub 3 is just 1. Okay? The degree is also going to tell us how many zeros and factors we have, the max number of factors and zeros we have, I should say, because it could have less, okay? It could have less real factors and zeros. So in this case, again, it's going to be equal to the degree, which in this case is 3. Our number of turning points, or max number of turning points, is going to be the same as the one before. It's going to be degree minus 1, or n minus 1, which in this case is 3 minus 1 equals 2. Okay, so this graph looks like it should be doing, let's see, we're going to follow our end behavior. It's down and then up, so let's keep that in mind. So down, up, okay, and ours is positive, so this looks like a pretty good end behavior to me. And it has at most 2 turning points. So maybe it looks something like, if we wanted to have, let's say we want to do not the 3 zeros, but maybe 2, just to make it interesting. So we'll do a 0 here, and we'll do 1 right here. So maybe this graph looks something like that. Oh, that's really ugly. Let me redo that. Maybe this graph looks something like this. There we go. And I should have done that in purple, but that's all right. So we can see by this picture, just to make sure we have everything we need to have to see if it's an okay sketch. Okay, pretend this is all one curve, okay? We have a 0 here, so that's 1 0. We have another 0, so it has 2 zeros, but as long as it's less than the degree that we have here, we're good to go. This actually is going to be a double 0 here if you know what that is, but if not, that's okay. We'll go over that a little bit later. Let's go ahead and label our turning points. We have one turning point here, and we have another turning point right here. So we are good to go in that place as well. And our end behavior is falling and then rising, which is okay as well because our degree is odd. So it should be doing kind of the opposite on one side compared to the other. And since it's positive, it's going to follow the same pattern as our original graph up here. Okay. But yeah, that's basically it. Hopefully you guys can go ahead and do your own 2 examples. There's 2 more examples you're going to have to do by yourself. If you have any questions, as always, just let us know. Thanks.